Hello and welcome to MT3 again, and this is our next topic in vector spaces, linear dependency. This is again a topic which you may have seen before, but let's have a look at what we are up to here. Now, I've got three cases of vectors. These are just the usual lines with direction vectors. In A, we have vectors A and B, which let's say are orthogonal to each other. Now, we haven't defined what orthogonal means yet, but you have an intuitive idea of what it is. And you know that these two vectors are linearly independent. They form a basis for this two-dimensional space. What makes them special? Well, you cannot represent A in terms of B or vice versa. Let's come to case B. Now, these two vectors again cannot be represented in terms of each other. I mean, there's a little bit of A which is along B or vice versa, but there's a little bit of A which is perpendicular to B. You can represent A in terms of a bit that's there and a bit that's here, and this part here is along B, but that part is orthogonal to B. So once again, A cannot be represented entirely in terms of B. But when we come to case C here, now we can see that vectors C and B are orthogonal and they can form a basis, and A can be represented as a linear combination of some part of C and some part of B. So intuitively, you've seen this before, that that this set here has one vector extra. I mean, it's the basis for this two-dimensional space, which is the plane of this sheet here, should consist of only two vectors. But we have three here. Therefore, that third one should be representable in terms of the other two. Now, what we want to do is formalize these ideas and put down a definition of what linear dependency is. Well, before coming down there, let's just put down the simpler idea of a linear combination. All right. So if we've got vectors A, B, C, let's not write A, B, and C. Let's call them A1, A2, all the way to AN. We've got n vectors here, and let's say I've got if I've got n scalars, so these vectors all belong to our space, our vector space, and let there exist scalars. Let's call them lambda 1, lambda 2, all the way to lambda n, and these scalars belong to our set of complex numbers. Now we can make a linear combination of these vectors by multiplying each by a scalar and adding them up. So we have lambda 1 times A1 plus lambda 2 times A2 plus dot 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 plus lambda n times AN. This combination of vectors is guaranteed to be a vector because of the axioms, and if you are unsure of this, go back and see which of the axioms should be used to assure us that this combination is a vector. So this belongs to our vector space, and this is called a linear combination. By the way, it was because this kind of a linear combination of vectors belongs to the same space. A vector space is often called a linear space or a linear vector space, and this goes back to the 1800s. All right, so we know this is a linear combination. Now let's try and see if we can understand what a linearly independent and linearly dependent set of vectors is. Right. So let's write down this linear combination in a short form first. So we can write this new vector as the sum I goes from 1 to n lambda I times AI. Alright, that's a short form for this thing here. Now if this linear combination, so it's a big if here, if this linear combination I goes from 1 to n of lambda I ai is equal to the 0 vector, and if not all lambda I are equal to 0, that means some lambda I is non-zero, then the set A1, A2, etc. is set to be linearly dependent. Alright, so what does this mean? Well, let's assume that one of these lambdas is non-zero. So suppose lambda n is non-zero. Okay, then what we can do is pull out the case I is equal to n from the sum. So let's write the sum in its full form. Then 0 is equal to, by the way, notice that I put the vector bar under here. It's not equal to 0. This 0 without a bar is a scalar. Alright, we need to ensure that our vectors are represented with this bar underneath. Now, it's not a fatal mistake if you forget about the bar, but you know, if you want it to be correct, you've got to have the bar there. The sum of vectors cannot be a scalar. Alright, so 0 is equal to lambda 1 a1 plus lambda 2 a2 plus all the way to lambda n a n plus, and this goes all the way to lambda, actually I have two n's here, so I'm going to change it to let's say a p there, a p there, and a p there. Now if this lambda p is non-zero, then I can divide by first of all pull out the ap to one side. So we have lambda p ap is equal to, I've got a minus sign there, lambda 1 a1 lambda 2 a2, and then we don't have a lambda p, so I'll just note it down. Plus all the way to lambda n a n, and I've forgotten the bar, so let's put them in there. There's a bar there. It's easy to forget the bars, but we should try not to. Alright, and now since lambda p is non-zero, we can divide by lambda p, and I'm going to divide by minus lambda p, so I have a positive coefficient there. So this gives us AP is equal to minus 1 over lambda p times lambda 1 a1 plus all the way to lambda n a n, where once again we note that lambda p ap is missing from the sum. Now one way of writing such a sum is to write it in a nice compact form as minus 1 over lambda p. The sum I goes from 1 to n, and we have a constraint on I is not equal to p. Lambda I. Okay, now what we have said here is that the vector AP is written as a linear combination of the other vectors, and that's what this means. So if you can if you can form a linear combination in this way, let me just go here. If you can form such a linear combination such that it's equal to 0, the 0 vector, and at least one of these coefficients, these scalars, is non-zero, then you can write the vector corresponding to that scalar, AP, as a linear combination of the other vectors, and this is what makes the set linearly dependent. The corollary is that if the only way to get this linear combination of vectors equal to the 0 vector is to have each of the scalars equal to 0, then the set of vectors is considered to be linearly independent. So let me say that again. If the only way you can have a linear combination of these vectors a1 to an with coefficients lambda 1, lambda 2 all the way to lambda n, if the only way you can have the sum equal to the 0 vector is to have the scalars lambda 1, lambda 2, etc. all equal to 0, then the set of vectors is called linearly independent. Okay, now with that with that definition in hand, let's see if we can work off some cases where vectors are linearly dependent or independent. I have a few examples here, so let me just find them. Okay, so example 1. Example 1. My vector A is equal to 1, 0, 1, and B is equal to 1, 1, 0. Are these linearly dependent or independent? How do we go about showing this? Well, the question is the 0 vector, I'll put a question mark there, is the 0 vector equal to, can it be equal to some alpha A plus beta B, where alpha and beta are scalars? All right. We want to see if we want to find out what choices we have to have for a alpha and beta such that this can be equal to 0. So this is a three-dimensional vector, so I have my 0 vector is itself 3 dimensions. So that's my column vector there. This is 0 vector, and the question is, can we have this equal to alpha times A? Now A is 1, 0, 1 plus beta times B, and B is 1, 1, 0. This itself is simply equal to alpha 0 alpha plus beta beta 0, and now we can add these two together to give us alpha plus beta as the first element in this vector, 0 plus beta, which is just beta, alpha plus 0, which is alpha. Now what this means then is that if I want to have an identity, if the 0 vector is got to be equal to this, then we must have, we just identify the terms. So 0 is equal to alpha plus beta, 0 is equal to beta, and 0 is equal to alpha. Well, what these two mean is that the solution is alpha 0 and beta 0. And therefore, the only way we can have an identity here that the 0 vector is equal to alpha A plus beta B is if alpha and beta are both 0. So since both coefficients are 0, therefore A and B, not beta, B, the set A and B is a set of linearly independent vectors. All right, nice and easy. Let's have a look at another one. A is 1 0, B is 5 0, C is 0 1. Now you know, you can say, okay, you know what the answer is going to be, but let's do it the long way. Yeah. So our question is going to be, is this, on what conditions do we have on the coefficients alpha A plus beta B plus gamma C such that this is equal to 0. So our 0 vector is 0 0. I'm going to do this quickly now. Alpha A is simply alpha 0 plus 5 beta 0 plus 0 gamma, which is alpha plus 5 beta, and in the second line we just have gamma. So the only way for this to be equal to the 0 vector is if 0 is equal to alpha plus 5 beta and 0 is equal to gamma. Alright, so that's one solution there. And what we have here is, therefore, alpha is equal to minus 5 beta, and from here it's just gamma is equal to 0. Alright, so we have no choice on the gamma. If we want this to be, if we want the sum of these three vectors in a linear combination of these three vectors to equal to the 0 vector, gamma must be 0. However, the only condition on alpha and beta is that alpha is equal to minus 5 beta. We could choose anything for beta. For example, you could choose beta is equal to 1, or in which case alpha is equal to minus 5, or you could choose beta is equal to 10, in which case alpha is equal to minus 50. It's up to you. The only thing we need to observe is that there are non-zero solutions to this equation, and therefore we have we have an infinite number of these non-zero solutions to this equation, such that this linear combination can be equal to the 0 vector. So this set of vectors is linearly dependent. Now you could see this, right? I mean, you could see right at the start that the vector A is simply, the vector B is simply 5 times the vector A. A and B are already linearly dependent. In fact, they are parallel vectors. C is orthogonal to both A and B, and therefore gamma had to be 0 if we wanted this to work out. But this is the way we find out if a set of vectors is linearly dependent or not. Now, before we finish, I'm going to leave you with one example. What about this set of vectors? A is equal to 1 0 and B is equal to 10 to the minus 300 0. Are they linearly dependent or not? And I'm going to ask you to think about it in two ways. One, would this be considered linearly dependent if you were... Okay, just think about it, okay? And let's stop here. Thank you. And the next topic we're going to be looking at is basis sets.